As we begin looking at this section, we begin by looking at measures of dispersion in section 2.4. One of those measures of dispersion is deviation from the mean. And when something has a deviation, that means it has a distance. We want to know how far away it is. So this one, we want to know how far is something from the mean. So if we have two numbers, let's say we have a set of data that has a mean of 6. If we have a data value of 8, 8 is 2 units from the mean. More specifically, 8 is 2 units above the mean, because if we think about a number line, if the mean is here, obviously 8 is larger than the mean, so 8 is 2 units above the mean. On the other hand, 4, we had a data value of 4. 4 is 2 units below the mean. So in order to calculate deviation from the mean, we take a data value minus the mean, and that difference will tell us how far a particular value is from the mean. So if we do 8 minus 6, we get a positive 2. 2 tells us how far from the mean it is. Positive tells us it's above. If we take our data value of 4 minus the mean 6, we get a negative 2. 2 again tells us how far, but the minus tells us that 4 is below the mean. So it is important to know what those signs mean. The positive means we're more than the mean. Negative means we're less than the mean. So if we have a set of data, let's suppose I give 7 people quizzes. Someone made a 5, someone made a 10, someone made a 7, an 8, a couple 9s, and a 6 out of 10. Let's find out the standard deviation, which is basically on average how far are these data values from the mean. So real quickly, if we want to know the mean, we add up those values and divide by, there are 7 data values, so we divide by 7. So I'm just going to pull out my calculator and do 5 plus 10 plus 7 plus 8 plus 9 plus another 9 plus 6. So 54 divided by 7. It's about 7.7, 7.71. Say about 7.7. So that's the average for that particular quiz. So notice some data values are below the mean, other data values are above the mean. So if we want to know on average how far are the data values from the mean, we calculate something known as a standard deviation. And what we actually calculate first, before we get the standard deviation, is known as the sample variance. And we're going to use the symbol S to stand for standard deviation. The sample variance is S squared. And it turns out we actually find S squared before we find S. Now there are 2 formulas that we could use to calculate variance. The first one that the text shows is they tell us to find all the deviations, find the deviation of each data point, square that deviation. In this notation here, that's called sigma. It means to add all of those up, and we'll illustrate what that means in a minute. So add up all of the deviations squared. So these are the deviations. It says square those deviations, and then add all of those up and divide by n minus 1. I'm not going to go into detail why it's n minus 1 and not n, but that's just basically averaging the square of the deviations. So that gives us variance. And then if we have variance and we want standard deviation, we take the square root of that, and that gives us standard deviation. Now, this formula is okay to use, but if you look back at our mean, notice our mean has a long list of decimals that doesn't end. Or, yeah, it eventually gets into a pattern. So, every time we calculate the deviation, we take a data value minus the mean. Notice each of those are going to have some error. If we do 5 minus 7.7, well, our mean was not exactly 7.7. So if we just calculate our deviation to be negative 2.7, well, that's not exactly right. That has a little bit of error in it. So each time we do data value minus the mean, data value minus the mean, and so forth, each of those are going to have some error. And then when we square it, then that's going to affect our error. So while this does give us the variance, depending on our data, we may have more or less error in calculating this variance. So there's an alternative formula, which is the one that I prefer you use. And that is if you take the sum of the x squareds minus the sum of the x's squared over n, then divide by n minus 1, that'll give you the sample variance. Now, let's look at the difference between these two. The sum of the x squareds, this one means square each data value, then get the total. This one means get the total, add all the data values, and then square your answer. So again, this one says square each data value, then add those up. So let's illustrate that by doing an example. Let's take this one, copy this data over. So the best thing to do is to organize our data and our values into columns. So I'm just going to list these. So our formula, we need to know the sum of the x's. We also need to know the sum of x squares. So I'm going to have an x squared column. And we're going to take each data value and square it. So 5 squared is 25. 10 squared is 100. 7 squared is 49. And so forth. So for our variance, remember we need the sum of the x squareds minus the sum of the x's, and that answer squared over n, all divided by n minus 1. So let's add these numbers. And we did that earlier, but we'll do it again. So summing our x's, that means add 5 plus 10 plus 7 so forth. So remember that was 54. And then summing our x squareds, that means add these numbers. So if we take our x squareds and add all those up, we get 25 plus 100 plus 49 plus 64 plus a couple of 81s. And that was supposed to be 36. 6. 6 squared is 36. When we add those up, we get 436. So if we fill in our formula, our variance is the sum of the x squareds. So this is the sum of the x squareds minus the sum of the x's. So the sum of the x's, that's 54. Then square that number, then divide by n. Remember, n is just the sample size. The number of data values we have, 1, 2, 3, 4, 5, 6, 7. And all of that's divided by n minus 1. So once we calculate this, this will give us our variance. So we have to be careful when we input this into our calculator, because if we try to put it all in our calculator at one time, remember our calculator is only as smart as the person putting things in. So if we tell it the wrong thing, then it's going to give us the wrong answer. Notice 54 gets squared, and then that gets divided by 7. We have to take that answer and subtract it from 436. So if you're careful with parentheses, you can put all of this in left or right and be okay. But if you're not careful, then you could end up getting something that's not equivalent to this expression. So if you're uncertain, then just take this a step at a time. Say, well, what is 54 squared? That's 2,916. On bottom, we can simplify that. Then say, well, what is 2,916 divided by 7? So that's what we're subtracting from 436. 416.57. And so forth. Now I'm going to keep all of those decimals in my calculator, so I'm going to say, well, that 416.57, that's negative, and then I'm going to combine that with a positive 436. So when I combine those, I get positive 19.42857. For writing it down, I'm just going to call that 19.43. That's going to be divided by 6. I'm actually going to leave all those decimals in my calculator, and then when I divide by 6, I get 3.238, etc. So that's the variance. And I guess if we're accurate, we would put squiggly lines to say that it's approximately that, because it's not exactly 3.238. We had to round. So that's our variance. So if we want to know our standard deviation, we take the square root of that. So the square root of a square, those cancel, giving us S. And if we take the square root of this number, 1.799. So our standard deviation is about 1.799. That is, on average, our data values are approximately 1.799 from the mean. Now, none of them are exactly that distance from our average, but if we take how far each data value is from the average, each deviation, and average out that deviation, then on average, that's about how far our points are from the mean. The larger our standard deviation is, the more spread out our set is. The smaller our standard deviation, the less spread out our set is. So if we had a standard deviation of 3 as compared to 1.799, that would mean that our data values are spread out farther. Where here, our data values are relatively close together. If we had a smaller standard deviation, then that would mean our data is grouped even closer. So the more spread out it is, the larger standard deviation. The smaller it is, the smaller standard deviation. So again, that's just describing how dispersed our data is.